You're gonna have a few lectures and try to keep each to 15 minutes or so. Students, you can feel free to interrupt here and there with questions or raise your hand, and we'll try to leave a few minutes at the end for questions as well. Can you see my screen? Am I sharing? No, share screen. Okay. Okay, so now we're good. You can see. Okay.
Yep.
So today we're going to be talking about compressional tectonics, and a lot of compressional tectonics that we see are in the Pacific Ocean and surrounding the Ring of Fire. So the Pacific Ocean has a variety of subduction zones, and that they have hosted many sizable and damaging earthquakes. And this includes the 1960 Valdivia earthquake in southern Chile. This was magnitude 9.1, and a 1964 9.2 earthquake in Alaska. Rich may talk about this as well. And you can see here I've shown in blue some earthquakes that people in this class sure have heard of, perhaps even studied. So this includes the 2010 magnitude 8.8 earthquake in Male in Chile, and the 2004 9.1 Sumatra earthquake in Indonesia. This earthquake really changed how the geologic community sees tsunamis and their hazard. And then is also the 2011 magnitude 9.1 Tohoku-Oku earthquake in Japan. It's also created a surprisingly large damaging tsunami. Also taught geoscientists a lot about how the upper plate deforms in these earthquakes. So yeah, the Pacific Ocean is home to the Ring of Fire and has these very large, quite damaging earthquakes and significant volcanism. We'll discuss today one of the primary geomorphic paleoseismic evidence of these subduction zone earthquakes is through relative sea level change, as well as liquefaction, tsunami deposits, and landslides. As we'll be looking in your Seattle assignment, there's a variety of other faults that are not these main subduction zone faults that can create a lot of hazard. And keep in mind, so the assignment you're looking on right now in Seattle is part of the Cascadia subduction zone. So again, keep in mind where you're looking, and that subduction tectonics describes the general tectonic environment of that area. It does not want to go to the next slide. Okay, and so the subduction zone earthquakes are big, and they have a large amount of slip. And so these two plots show a fault plane that slipped during the earthquake, and the fault plane is colored by the amount of slip. And so this is looking at the 2010 Male earthquake in Chile, and this is looking at the earthquake the year later in Japan. So I'd like you to look at one or of these and take a few seconds and determine both what was the maximum slip during that earthquake as well as the rupture length. Give you maybe 30 seconds, and then you can put it in the chat or say out loud. right, one chat, few chats. So Christy says, yeah, the max slip in Tohoku is about 70 meters. And yes, but as Ramon says, best to hear from the students first. So let's start with Chile then. Is everyone shy? Is everyone awake? Jumping jacks time?
One comment from UNR class here is the length appears similar, and that the 2010 earthquake seems a little longer. And so my question to everybody else would be why is that?
Also, let's start with more of the observations. So what is the length of the Mali earthquake? At least looking at this figure. So Aaron says 2 degrees. So yeah, it's about right. If you look at the red here, which is about 10 meters of slip, you see that it covered 2 degrees of latitude. So it's 220 kilometers of very high slip. But if you go to include more of the yellow, then it's maybe 4 degrees of latitude, 3 or 4. And so the length of the fault that slipped is maybe 300 to 400 kilometers. And then for Japan, I want to have an answer from someone else. So we see a somewhat similar pattern of about 2 degrees of latitude of very concentrated slip, in this case up to 20 meters, but the full fault plane itself is about 4 degrees of latitude, so about 400 kilometers. And there's some variation on exactly where in the far field you allow the fault plane to stop. But we see that the the fault plane that slips in these subduction zone earthquakes are very large. And that's one feature that, as we'll see, is really important for reading the paleoseismic evidence created by these earthquakes. So here we're looking at the profile of a subduction zone. And in blue, highlighted where these areas are for Seattle, where your assignment is to give you a little bit more context. So in Seattle, the Juan de Fuca plate is subducting under the North American plate. And here is what the subduction zone looks like. We have the trench here. This upper portion of the subducting plate is locked. And when it slips, that's what generates these big earthquakes. The region between the trench and the volcanic arc is called the forearc. And that includes a fold and thrust belt, coast ranges, forearc basin. In Seattle, you may know of Mount Olympus, and this is part of the coastal ranges. And Seattle is in the forearc basin, as are many other major cities around the Pacific Ocean. And then we have Mount Rainier volcano, which is immediately to the east of Seattle. So understanding the seismic cycle is really important for then understanding the paleoseismic evidence for subduction zones. And so here shows we have a subducting plate and the overriding continental plate. And during the interseismic period, which is shown here, the plates are locked this section. And so the subducting plate pushes, so it causes elastic strain accumulation, as well as uplift here of this area along the coast and shortening here in the forearc area. And the interseismic period lasts on the order of 300 years. And so at least on the earthquake cycle, this process is fairly slow. Then we have coseismic period, and many subduction zone areas have big earthquakes about every 300 years. During the coseismic, there's a slip here, and all the accumulated strain is released, and this causes subsidence here along the coast and an extension in the forearc region. So we can see evidence for both of these processes in the paleoseismic or geomorphic record, which I'll discuss. And so the evidence for that subsidence right along the coast is from a phenomenon called killed trees. And this is where trees that were along the coastline essentially die very quickly from this instantaneous subsidence. And so here we see a tree that then very quickly is subsided due to coseismic slip from a large or great or megathrust subduction zone earthquake. And other evidence that we might see along with the, then the tree will typically die within a year or two following stunted growth. We also will often see tsunami deposits, liquefaction, as well as a general change from terrestrial setting to an intertidal setting. And one of the key pieces of evidence for linking these trees to earthquakes is that they occur over a spatially extensive area. So when we're looking at the Chile and Japan earthquakes, saw that there's substantial slip over 2 degrees of latitude. And so we would expect that this phenomenon of these killed trees is spatially extensive and not focused to a small area. So here's an example of this phenomenon happening in Alaska. This is following the 1964 earthquake, where the trees that were instantaneously submerged grew for 1 to 2 more years, and then they died, and radiocarbon dating can help to determine the timing of this. As well, method has been used for the 1970 Cascadia earthquake for assessing the timing, location, and size of that earthquake. And then, so then also showed that there's this extension here in the forearc, and this extension can be recorded both with remote sensing and with geomorphology. So one of the questions in the reading was, how can we use remote sensing to see some of these features? So this is looking at geodesy, GPS. Remote sensing can be used in a similar way. So here we're looking at extension. So each of these arrows shows the GPS displacement during a 2004 earthquake in Chile. And you see that these arrows near the coast are longer than these arrows inland. And so that tells you the area near the coast moved to the west more than the areas inland, and that this forearc region experienced extension. So the And then this extension is also recorded in the landscape. It's actually a project from my PhD thesis, where in the very, very dry desert of the Atacama of northern Chile, these fractures form that record the extension of the upper plates during the earthquake. So that is the end of my presentation. I'll take one or two questions, or perhaps we should move on. Are there any student questions about the presentation?
Yes, I actually have a question.
Yeah.
So could you describe more in detail the photograph representing surface fractures? Because I'm not sure I get it.
Yeah, so these are fractures in the Atacama Desert of northern Chile, where it's very, very dry. And these fractures open during the earthquake, and they're mode 1 fractures. So they represent extension of the crust, or the very, very upper portion of the crust. It's concentrated on these fractures. And so these images were taken right after this 2014 earthquake. And we know that they opened right after the earthquake because they preserve these very sharp corners or edges, which wouldn't persist for very long otherwise. And so they represent this opening of the extension of the upper plate following the earthquake.
Thank you.
All right, let's move on. I think Rich.
Sure, can I share screen?
You should be able to.
Can you see my screen?
We can see it.
Okay. Okay, so thanks for that, Chelsea. It's a nice introduction to the Ring of Fire. I'm going to talk a little bit for the next 10 or 15 minutes or so on reverse and thrust faults in Alaska. And it just shows some examples of a couple studies where we can see the geomorphic expression of active deformation. So Alaska has a lot of faults. It's the most seismically active state in the Union. Chelsea was talking about the Ring of Fire. So the Aleutian subduction zone is there on the bottom across the Aleutian Islands and coming up into south central Alaska. Pacific plate is subducting at about 5.5 centimeters per year into the North American plate, basically exerting compressional stresses into hundreds of kilometers away from the subduction front into Alaska. So some of the main fold and thrust belts are the Chugach St. Elias Mountains here in South Alaska, and there's reverse faults in the Four Arc Basin here, the Castle Mountain Fault, and then the whole north side of the Alaska Range, which contains Mount McKinley and Denali. It's a massive mountain range, is bound by a broad fold and thrust belt on its northern side. So the takeaway is that the reverse faults can exist hundreds of kilometers inland from the subduction zone. So the Castle Mountain Fault is in the Four Arc near, so here's Anchorage on this map here for reference. And I'll show some mapping in this box here. But basically, it's expressed in the topography by a nice vegetation lineament in a lot of places. So this photo in the middle shows deciduous trees that are growing on well-drained, uplifted part of the topography, whereas they can't grow in this boggy, wet areas down here in the downdrop side. So here's an excavation across the Castle Mountain Fault. It shows a north dipping fault plane and sort of some thrust soils. Here's a seismic line that goes across the fault that shows a north dipping fault sort of flowering up towards the surface. So the geophysical data shows us that it's a reverse fault. For many years, for decades, it was thought it was a strike slip fault, but we tried to investigate that. So here's an image at the top and a hillshade in the middle and a geologic map. It's kind of hard to see, but the fault is mapped across just the middle of the image here. And the point to take away is that it's hard to see the fault in a lot of areas because this is really young glacial outwash deposit. There's a moraine here in the middle, and you can see in the topography that's in purple. And I'll zoom in a second, and we'll show some of the features that help us sort of understand where the fault is. But similar to what we were talking about in class the other day about taking observations and making points along the fault, we did that on the imagery across this whole image, and then we also went to the field and looked at all these features. So I'll show you some examples of that. So here's what it looks like in the field. So the nice reverse scarp here. Here's some geologists for scale. So the scarp is sitting in here. It varies in height from about 1 meter to about 3 meters. But the notable thing is it's consistent all the way across. It steps and bends a little bit, but all the way across that map that I was showing is just consistently up on the north. When we get in and look at some details, so here's some slope shades, some slope maps, and some LiDAR imagery. The 3 pictures on the top is the same area. So you notice this shadow going across the center of the photo here. And another interesting thing is sort of this en echelon pattern. My pointer's not really working very well. An echelon pattern, you can see it really clearly in the yellow here. So there's a south-facing scarp, but there's also en echelon fractures across the face of the scarp. So it indicates a bit of oblique motion. Left stepping en echelon features are typical of right lateral strike slip fault, so it suggests a component of right oblique motion, but it's dominantly up on the north, indicating reverse motion. Another thing to notice is north of the scarp are these sort of parallel yellow slopes highlighted here that are parallel each other. Those are actually grabens, so it's a typical feature that we see on reverse faults. The fault will move and cause some folding in the hanging wall, and that folding is expressed at the surface by grabens that form in the crest of the anticline. You can see them also in the slope shade on the left, but my pointer doesn't want to go over there. But they're really pretty clear here. Here's just sort of an oblique view of that same feature, just showing how the scarp is consistently up on the north side. And then when we look in a little more detail, you get sort of the scarp here, and then distributed scarps, going up over the folded surface. And so that's shown here in this profile with some sort of schematic faults coming up to each of the scarps. So there's a frontal scarp, and then this is somewhat of the extension in the folded crest of the anticline that's causing these scarps. These 2 images on the bottom right are the same. This just shows the satellite image, shows how many trees are there in the Little Susitna River Valley. Really difficult to pick out the fault. But when we get the hillshade, we see again consistently south-facing scarp cutting across fluvial terraces. Old meander scars here from glacial outwash, but a nice scar. And so when we walk across that Castle Mountain Fault, we see lots of different expression of the scarps, and it's really similar to especially the Osceolar Fault in New Zealand, where it's a similar sort of landscape with glacial outwash deposits, and it has had a few earthquakes. And so you get this nice step in the system. You get a fold on the side of the scarp here. You get small fractures that are sort of connecting the step. These are typical features that we see along reverse faults. And then the 1980 El Azman, Algeria earthquake, and the Armenia earthquake in 1988. These are some studies from the 80s and 90s that just show the variability in the scarp, in the shape of the scarp, as you go along strike. And on the Castle Mountain Fault, we saw vestiges of all these types of scarps along. And then the one at the top, you notice these N echelon features I was showing on the slope map on the Castle Mountain Fault previously. And Chelsea, let me know when I get to 15 minutes. I don't want to take time away from Chris and Ramon. So then the northern foothills, fold and thrust belt I mentioned bounds the north side of the Alaska range. So here's Mount McKinley, Denali for reference, and the mountain range is a sort of south arcuate south-facing range. And then all these black faults up here bound the north side of the range, and it's this pretty wide zone of thrust, back thrust, and reverse faults. It gets a bit wider towards the west. But what you can notice from the DEM here is that the faults sort of bound mountain ranges. There's a little east-west trending small mountain ranges that are north of the main mountain range. And so the faults are, I don't know why my pointer keeps going away. So they bound these sort of pseudo range fronts that are north of the main range of the range. Here's a picture of it. So this picture is the northernmost one up here. This is the main northern foothills thrust, and it's just a massive 100 meters high or so escarpment. This is a flat terrace surface of Pliocene gravels, and this is what it looks like in the field from a helicopter with the scarp running along the yellow arrows there. So here's the geologic map of the north side. Interesting thing to note here is the rivers cut through these sort of east-west trending ranges that are bound by thrust and reverse faults, and they're basically anticlines, these ridges, and the rivers cut through them. So as progressive deformation grows these ranges, the rivers keep cutting through them. Here's the Nenana gravel I was mentioning in tan, and then younger glacial outwash in the other colors, and then modern river terraces. And so Sean Bemis profiled these. When you notice the tan here on this profile is deformed over these anticlines out to the front. Out here is where the picture I showed on the last slide was. And then the younger terraces are deformed a lesser amount. So it just shows progressive deformation through time. Here's a cross section of that going across the Alaska range. So the basal thrust up to the northern foothills main thrust, and then a bunch of back thrusts and reverse faults. One of those is the Park Road fault here. I'll show an example of that in a second. So here's the Park Road fault. This is what it looks like on a hillshade. There's like a landslide up here, a nice scarp, and sort of some deformation in the hanging wall. Deformation in the hanging wall can be seen also on this profile, where you have just like little grobens on the fold above the fault. And here's some geologists sitting in those grobens. They're about 1 meter or 2 deep. And then here's the front of the scarp here, which runs across the hillshade image here in red. And then this is a really neat feature. We call it the giant mole track anticline. It's sort of best viewed in this hillshade where you see these small hills going along sort of in a curvilinear fashion, but it's outboard of the main range front, which is these steep drainages over here. This giant anticline is outboard of the main range front. Here's some profiles of it. Here's a picture from a helicopter of it. Now let's see, how was the best way to see it? So here's the crest of the anticline here, and here's the thrust at the base of the hills there. So these hills in between the crest of the anticline and the front of the thrust are what's shown in the hillshade of these little pieces of mole track. And this white is a tarp that's in the fold of the hanging wall anticline, and here's a trench exposure at the tarp covering the trench exposure. And what you find there are some normal faults in the crest and evidence of older earthquakes with colluvium filling that. So every time there's an earthquake, it opens up a little bit on the crest of the anticline with little normal displacement. So thrust displacement on the front, normal displacements on the hanging wall. This is a massive feature that goes through the landscape. How am I doing on time, Chelsea?
About 2 minutes, and then let's have 1 more 2 minutes for questions.
Okay, that sounds good. So I have a couple other slides here that were just sort of extras, but back to the Castle Mountain Fault, one thing you notice is that some places you can't really see the scarp. You can kind of see an indication coming through here, and maybe something in here, but not really much in here, but it's right on strike and it's right in a zone where there's sort of a step in the system. If we do a profile across that, you see this here. So sometimes the fault can be blind at the front of the thrust, and all you see is really an anticline. So this is about 3 kilometers long, so it's a broad fold in sort of a young surface. So the last earthquake along there was about 5,000 years ago, and these sediments are about 13,000 years ago. So it's only really experienced, one major earthquake, possibly a second one, but I won't talk about that. And then just a final example, here's the Alaska Range near the Mole Track anticline, a little bit further to the west, but there's a range front along here between the arrows. And then, so a longer term displacement is expressed in this big sort of shadowed area that's higher. But then if you look closely, there's another scarp that runs through here. Here's a picture of that area, so really steep topography, showing progressive offset. And then trenches across here just show like basically the folding I was talking about. So this part has come up and then sediment sort of deposited against it. And that's all I really have. Take questions, or I can wait till the end as well. Just want to leave time for the other professors.
Maybe 1 or 2 questions from students, and then if not, Christy, put a question in the chat.
Rich, could you go back to the previous slide and explain that subtle anticline?
This year. Yeah, so the fault runs basically east-west across this image. You can kind of project it along my cursor here. You get to the zone where you don't really see much deformation. So the deformation where there's this little scarp here is kind of concentrated right on the front of the thrust, which would be kind of, this is sort of a cartoon of it. But we don't really see a nice scarp in the topography here, which is sort of a younger drainage. So the sediments are younger, and there's also a step in the system there. And so instead of making a scarp all the way across, as the rupture sort of makes its way through the step, it's causing folding in this area. So this is about 3 kilometers long here, and the profile of the, a river profile should go down, right? Downstream, but it doesn't. So there's some ponding up above here, and this former channel is basically now abandoned. It's a glacial outwash channel, and the result is this fold in the topography. And so it's going up on the north side and causing that fold. Does that answer that?
Yeah, thank you.
You want to answer Christy's question, which is essentially, where do you map a scarp? Or where do you
where?
put the physical line?
Well, I'm just wondering if the scarp as a topographic feature might not always be co-located with like the fault trace as the surface intersection of the fault plane. And like, I know what you map is what you see, right? So you probably map the scarp.
Yeah,
But
I mean, sometimes it's blind, but where there is a scarp, the fault comes to the surface. But where it's blind, it may not come to the surface. And then it's also associated with a bunch of steps and bends and things like that. So mapping it and following it across the topography can be sometimes challenging. So when we have great data like hillshades and stuff, it makes it a bit easier to follow, but we don't always have that luxury.
Right. Yeah, because like if you map the topographic feature and then you try to do like a 3-point problem on it, you would not end up with the strike and dip of the fault.
Right, and the dip, I mean, usually it deepens up towards the surface as well. So you may not, if you see it in the trench or something like that, you may not have the full.
Right. Do these, like in a trench, do you always see them increasing in number of strands toward the surface, or do you ever see them like coalescing into fewer strands toward the surface if the most tip of the surface is the youngest part of the fault and is maybe propagating into
Kind of depends on
less.
the age of the sediment. So the less consolidated the sediments are, it tends to break up into numerous strands coming through. But if it's
Okay.
bedrock or some really consolidated sediments, you may get a single fault plane coming through the surface.
Okay, thanks.
All right, let's move on to Chris.
Okay,
Let me stop my share.
I think this is it. Okay, can everyone see my slides and hear me
Yes.
okay? Okay,
Yep.
so let me start my timer here because this may go long. I didn't pare down my slides from last time. So I'm going to show 3 different thrust fault examples and highlight some geomorphic features that are of interest that help define the fault and that you may want to keep in mind when you're mapping thrust faults in this class. So the first example is the Plato thrust. This is at the southern end of the Central Valley in California. You may be familiar with this if you've driven up or down the I-5. There's the grapevine, which marks the transition between the flat of the valley and the San Emigdio Mountains to the south. And you get reverse faulting here because of the Big Bend and the San Andreas Fault. So we think of California as primarily strike slip territory. But in this area, and also in LA, because of this big compressional bend in the San Andreas, you get reverse faulting. And so if this were one of the mapping assignments for the class, here's an image of the range front. Here's I-5 right here, what I was just talking about, going from the Central Valley into the mountains here. And just the first order observation is that things change right here along my cursor. So you've got a range front. So mountains here, flat of the valley here, incised drainages to the south. You can see where all the drainages exit the mountain front here, and you've got a bunch of fans. But if I had a crayon and this image, I'd just draw a fault along here. That's just the first order observation. And so this is from the USGS fault and fold database. This is the map of the Plato thrust. This is the equivalent of drawing the fault in with the crayon because the resolution isn't that good. You're supposed to be looking at it from really far away, not mapping things through your house or something like that. The scale isn't correct. This is where the thrust fault is. It's uplifting the mountains and bringing them up and over the valley. And you may have heard of the Wheeler Ridge. That's up to the north. That's the famous area where this fault is jumped out into the valley. If you had really high resolution imagery, or you could go to the field, then you'd see more subtle features. So here in this picture in the upper left, I can see maybe some terraces. This is potentially uplifted fan. You could see a subtle scarp right here, and you can see incision into that scarp. So this is pretty good smoking gun for where the fault would be. This is an oblique view, and we were just looking at this area to the right here. So that's where that really nice scarp was. You can see the mountains on the left, everything's incised, looks uplifted. It's pretty sharp range front right here, but then as we get over in the foreground, we can still see there's the transition between the valley and the range, but things are a little bit more subtle, especially in this area. And there's something going on here. I don't know if you can see it with your geomorphic eyes, but there's a landslide here. So here's the bowl, here's another bowl, here's all the material that came down. And maybe during some earthquake, there was a mega slide that came down and covered the fault. So the fault is now buried here. It may have been refaulted, but the point here is that on reverse faults in the hanging wall, you usually get really trashed rock. It's really crushed up and deformed, and it weakens it. And a lot of times along big thrust faults, you'll find landslides. That doesn't mean that every range where you find a whole bunch of landslides at the front, that means that there's necessarily a thrust fault there. But if you know you're mapping a thrust fault, you might want to keep that in mind, that there could be landslides and there could be landslides covering the trace of the fault. So what you may be mapping is not necessarily the fault in some areas, it could be the toe of a slide. And so this is a picture I took on one of many trips down. This is that same bowl right here. Here's the slide mass. And this is just fallen out and fallen on top of the fault. And it looks like it could be refaulted and uplifted. It looks like there's almost some terraces here. I'm not that familiar with the details of the geomorphology here, other than just driving along and seeing this every time that I go by. And so here's a geologic map of the range front. So the first area that I was showing you was this really nice sharp range front with the scarps and the uplifted terraces. So the fault is mapped right at the range front here. And then on this side, here's the big slide mass, and the fault is dashed or dotted beneath the slide right there. There's actually another feature here. You can see that lineament, that break in slope, and it's continuing along here. And you notice the change in the bedrock. So here we've got different vegetation. It's smoother. Here it's more in size. So these are, this is a Cretaceous unit. This is tertiary sediments. And that fault is right here. So you can see that in the geomorphology as well. The second example is in the vicinity of Muzaffarabad in Pakistan. A big earthquake happened here, magnitude 7.6 in 2005. And if you're familiar with the Indian plate crashing into Eurasia, here's the Himalayan arc in the upper left. And this is a little bit north of that. In this syntaxis here, everything gets really complicated, but geologically, but there's a big thrust fault coming up here. What's considered the active frontal deformation zone is here to the south, and this occurred to the north of that, which got lots of people excited. It was a 70-kilometer long rupture, east dipping reverse fault. So here's epicenter, it's rupturing up to the left here. And I'm gonna zoom into where this star is right here. And so this is the hanging wall at the top and the footwall at the bottom. And this image is from before the earthquake happened. This is Google imagery from before the earthquake. But you can see faults running along here that, again, there's landslides and rock falls in the hanging wall of the fault. It's all been crushed up. So I'll show you a picture here right after the earthquake. So in the hanging wall, there's Precambrian limestone. And you can see it in big cliff exposures here. And all these cliffs failed and had huge rock avalanches and landslides. Everything here, that's all landslides. So everything that's kind of gray or white, those are all landslides in the hanging wall, obscuring a lot of the fault trace right here. The next photo I'm going to show you is where the fault actually bends right here. You see this river is flowing along here. It may not always have that same path. It may have flowed here. Looks like there's a terrace riser here. but the fault is cutting across it. So it's going to uplift and preserve these terraces. And that's something else that you may want to look at or look for in your mapping. So here's that river that I was just showing you, bending around. And actually all those previous channels that I was showing you are here. And so these are marked as terraces in a paper by Kaneda. So here's the oldest T1 terrace. Here's the youngest T5 terrace. And the fault is running right along there. And it's preserving this whole staircase, a staircase of terraces along here. And then these pictures down here, I think they're right in this area here. So you can see the composite scarp, so from many earthquakes, and then you can see the more recent scarp from the most recent earthquake right here. And then here's a close-up of that. Another thing that I wanted to highlight, this goes back to what I was saying, that the rocks in the hanging wall get really trashed over multiple earthquakes, and you have higher ground motions there. So this is another part of the fault. Fault is running along here. It's dipping to the south. So the hanging wall is on the bottom of this picture, footwall is on the top. And unfortunately, all the white areas in this picture are damaged or destroyed houses that were sitting on the hanging wall. And then you can see right on the other side of the fault, most of the houses, they still have sharp edges. They're not really damaged or destroyed. And so here's a close-up of Balakote Hill right here. Almost every house on top of that hill was destroyed due to the high ground motions in the hanging wall. So again, that's what triggers some of these landslides along the thrust faults, and what can cause a lot of damage to infrastructure on the hanging wall, and what weakens the rock on the hanging wall. So the last example is from the Kaikoura earthquake in 2016. This was a huge multi-fault rupture, magnitude 7.8, and I lost track of all the count of all the faults that ruptured in this. It was more than 25, 200-kilometer long rupture, and a lot of it was strike slip. So in this map here, this is strike slip and strike slip, but I spent my time on this little section down here, which is the Papatia fault, and it was a reverse fault. And so here's the geologic map of the strike slip faulting that I was showing you. It's up here. There's the Papatia fault. It's separating Cretaceous, Oligocene rocks from Miocene rock, and then there's a lot of quaternary material related to the Clarence River right here. And what's interesting about this is the river ran along the fault. So I'm going to show you some pictures of the geomorphic impact that the rupture had on the river, and then I'll move down to the south and show you some pictures down here. So here's the Clarence River here, river valley. So you can see all these old channels in the LiDAR here. And then here's the rupture. And right here, the river was coming along before the rupture, was its channel at the time, but the rupture created an instant dam several meters high and diverted the entire river to flow down here and create this lake. It ponded and then eventually broke through here and continued flowing. And so I'll show you some pictures of that. So this is the old course of the river here. And here's where the instant dam occurred. And here's the new course of the river. And you can see the rupture, the thrust faulting in the river valley right along here. To the right, here's a picture of the scarp with the person sitting next to it. It's just sands and gravels. It's not indurated at all. So it's going to be reworked and removed pretty quickly and won't be preserved in the landscape. Here's the scarp right here along that temporary lake. And then here's the outlet of that lake. But you can see nice scarps in sand. Won't last long. Further to the south, going back to my landslide theme, there was a kilometer-long landslide in the hanging wall. The fault's coming along here at the base of the mountains, and then there was another strand up here. What's really cool is you can see the fault in the side scarp of the landslide. The white material here is limestone, totally crushed in the hanging wall, and that's why it failed. And so you can see one fault strand coming up here, another fault strand coming up here. This was a really famous landslide right after the earthquake because there were a bunch of cows trapped in the landslide. And so there were pictures on the news of cows on little rafted pieces of landslide debris that had to be rescued by dozer and helicopter. But back to my theme, you just have huge landslides here. And the fault is basically buried in this area. A little bit further to the south, the landslide that we were just looking at is up here at the top of this picture. And I like this image because it shows the reverse faulting, the impact of the reverse faulting on different landscapes. So here we've got the big mountains and the hanging wall, and here's the footwall. And then here, the fault is coming out into the ocean, right where the red arrow is. There's a secondary fault in the hanging wall that you can see right here. But this marine platform has been uplifted by the reverse fault motion here, and it'll eventually be planed down. Here's the secondary fault right here. This isn't the reverse fault. So I'm out of time, but just wanted to share you some things to consider when you're mapping reverse faults.
Thank you, Chris. Do you have time for a question or two if there are from students? Christy?
Thanks, Chelsea. This harkens back to like other things that have happened at meetings, but there's this Sakugen gravitational deformation of the surface associated by or triggered by faulting, often spatially coincident with the faults. And I'm struggling to understand when you're looking at a fault and you've got landslides along the fault, like how do you distinguish that from a Sakugen? Is that an important distinction? It seems like something people argue about at SCEC.
So I view it's a Sakugen I view as kind of a ridgetop failure rather than failure on the flanks of a slope. So actually, I did a bunch of consulting work in the mountains just north of my first example, and there were Sakugen there. And so you see the ridge top, and then you see basically grabens form at the ridge top as the ridge is basically pulling apart and collapsing on either side. Those weren't necessarily in the hanging wall of a fault. They're related to ground motions, high ground motions. And a lot of times you get ground motions amplified at ridge tops. If you think of kind of like a shaking tree, it's whipping back and forth, at the top. And so you're getting that ridge top shattering and collapse there. So those can happen all over the place. And I guess.
Is that distinguishable from something like an arête or a glacial feature where you have an over steepened narrow ridge lines that often collapse from the top? Or
I'm not familiar with glacial features.
I think we should move on though. We have one more.
Sorry, thanks.
In 15 minutes.
Okay, can you hear me now? Sorry about that.
Yes.
Oops, hold on just 1 second. Screen 2. Okay, so do you see a PowerPoint?
Yes.
Okay, so what I want to talk about is some examples from Central Asia for some more reverse fault phenomenology. I think for the students, what you really want to be taking away from this is these examples kind of as anecdotes. So, how is it that the faulting is interpreted based on the ensemble of features that are presented? Sometimes it's easy. Sometimes, like Christy's saying, it can be quite challenging. So, that's why we're doing it this way. But that's also why we teach you the GIR and morphologic mapping is again, you might say, I didn't see any of that. But if you go back to your basics, you can start to build. Can you guys hear me okay?
Yep.
Yeah, sorry, I just something froze there. I'll just keep going. So anyway, so I'm going to go to Central Asia. So this is the area, countries of Kazakhstan, Kyrgyzstan, Uzbekistan, Tajikistan, and China. And it's the area where the Pamir in the south are converging relative to the Tian Shan, mostly activating a lot of pre-existing structure that was developed in the Paleozoic as Eurasia was assembled. This deformation is still driven by the India-Eurasia collision, even though it's 1,000 kilometers in the continental interior. And so there's a lot of interesting questions about earthquake recurrence in these kinds of settings, where we have big faults, but relatively low slip rates. But that's not so much what I'm going to talk about today. I'm going to try to talk about the geomorphology along these fault zones as a guide for you for future mapping. So a lot of the work was done by was published recently in this paper by Magda Patiniak about the Pamir frontal thrust fault. So you can see in the lower left this view towards the big mountains. So the mountain at the top on the left is called Peak Lenin, and then on the right is Peak Dzerzhinsky. And so they're former Soviet heroes or anti-heroes, and there's a big reverse fault at the base of the mountain front. So this is a kind of a well situated fault geomorphically that's pretty easy to identify. And so you can see on the right a couple of the different maps that we presented in this paper. And so the T's are sites where Magda was, we did some excavations over time to zoom in. And I won't talk so much about the trenching, but try to emphasize, as I said, the geomorph and the setting of this fault system. And just to prelude a little bit, so that the frontal thrust is there deforming the Piedmont. There's a second fault further up in the thrust fault stack that we thought for a long time was inactive, but may actually show some activity. So it's important to not look for just a single trace. So we're going to move kind of along the mountain front to look at a couple of these sites, kind of zooming in. So here is this place, Achiksu and Ilaisu, which is in the western part of the zone. And so here you see really beautiful scarps deforming these fluvial terraces and fan units. And that's what we have in gray is mapped a couple of different terrace levels. So they're basically forming by kind of periglacial outwash in the mid to early Holocene. And so they're kind of aggrading, making these big fan surfaces, and then they're cutting down. So that's what the darker gray might show. And then those surfaces are deformed by repeated deformation. So the thrust fault's at the front, but then there's also some secondary structures like we've seen today with this rupture kind of sitting up high in the hanging wall here. And these little zones, these little splotches are places where we had structure for motion coverage. So here's moving to a couple more sites. You can see the Komensu on the top here is the same kind of situation with imagery and this sharp little fault trace cutting across these fluvial terraces. What's interesting is as we see going to the upper right there, the rupture trace moves into a moraine. And that hummocky terrain actually makes it a fair bit more difficult to track the fault trace. And then the bottom one here, Tashkungay, shows a little step here. So we see the one fault trace coming in from the west and cutting into the hanging wall some, and we sort of lose it, and then we pick it up again the next valley over. And so this kind of en echelon faulting we can see in reverse faults. And I'll show a couple of figures an excavation from Tashkengay in a moment. So here's just some pictures from the field to show some of these sites. So and most of them where we had made excavations. You can see on these are basically sort of 5 to 10 meter high scarps cut into these, as I said, like 7,000-year-old, mostly that's the age of this QT3 surface, fluvial terraces. And what's interesting, you see in the middle row is actually some of these are double scarps. And so we were kind of confused by this. Why is it double? We still don't have an answer, but it's definitely double in the excavation. So I'll show you what that looks like in a moment. And then here you see the trench on the lower right there where we see we're pushing these gravels up and over some of this colluvial material that is accumulating in front of the advancing scarp or advancing fault tip. So here's just one excavation, and the main point is to demonstrate that there is these two fault surfaces that are activating probably at the same time, and that's what gives us these double scarps, which add significantly to the complexity of the interpretation. But basically the gray on the logs is that fluvial material, and then the yellows are the colluvial material that accumulates in front of the scarp, and then the red would be the fault surface. So here's just a mapping from this summer with Ben and Ian. We were out there, and I'm showing Strabo spot output. So it's our tablet-based mapping system, and we spend a lot of time in Altadar where there's more of what we think a little bit more of a strike slip pattern of deformation, which I won't really speak about that much right now, but you can see the lines or some of my traces from this summer's work. The red would be faults and the blue are some of the moraine features that I noted. And then as we go to the main mountain front, there's more fault than is mapped. But if you look over here in Tashkengay, what you can see is there's the mountain front fault that I've showed already, but there's a zone of interest that we had that was higher in the range, and that's shown on the lower right. It's kind of an ugly hillshade, but you can see some disruption of the landforms there. But when we got a drone up in the air, we could look to the west and see this really spectacular scarp that breaks across this fairly complex alpine landscape, and you see it just sort of popping the ridge and going up higher. And then if we turn the drone around to look to the east, you can see the same trace goes over this moraine and then goes up onto this high surface where the scarp is as much as 35 meters high. So this is a much older surface that's showing continuous deformation. And then even behind is the probably inactive thrust here pushing the Cretaceous over the Neogene. Here's just a quick commercial for some technology. So here's Ian Pierce with 2 drones in the air. You see 2 controllers. He can sit in his buhanka and both of them fly and have PPK correction. And so also terrain following. So it's really spectacular mapping of this fault zone that kind of stay tuned. So then moving on from the Pamir frontal thrust in its kind of classic area, we'll take a quick look at this zone where there's a concentration of purple dots. This is a Nura earthquake that occurred in kind of the eastern Pamirs. It's not really on the frontal thrust. It's sort of stuck in the middle of this big pile of faults that are coming together as this valley's kind of closing by the convergent deformation. And there was an earthquake in 2008 that still has preserved a really nice surface rupture that we studied. And so here you can see the team. This is work I've done with the German colleagues at University of Potsdam. You see Manfred Strucker there and Magda Patiniak, she's drinking her beverage. And then Alana Williams is one of our students. And then our Kyrgyz colleagues are here. And behind them then is the fault zone. This is also right near the Kyrgyz or former Soviet Union Chinese frontier zone. So that hole right there is actually a howitzer emplacement, sort of field artillery for sort of former times of the Cold War. And it's exactly right where the thrust fault is tracing. If I just draw it, this is a reverse fault, not really thrust anymore. But it goes through just behind that zone. I can't seem to annotate right now for some reason. Are you guys looking at the main screen, or which screen is being shared?
It's You guys hanging out? Lunchtime.
Yeah, okay, but it's the full screen, not the PowerPoint like helper side, right? Okay, sorry. Anyway, so here's just a quick view of the fault zone in different views of topography. So just a quick lesson on resolution. So you can see 90 meters going down to 10 meters per pixel. We can see more. And so you see what's interesting about this fault trace is it's really not at all at a mountain front. It's just right along the side of this valley. And so we have basically reverse faulting that's driving the downhill side upward. So this is really notable for a lot of uphill facing scarps. And so if I don't know if you guys can see this video, if it plays very well, but this is a view over the rupture, and I'll just pause it. But what you can see is this really distributed cracking. But what's useful to see, if you can see my cursor, is we see the right side is being lifted up, and the right side uplift in this earthquake, which is defined by the fracturing, might be 50 centimeters to a meter, but the scarps here are higher, indicating that this zone has seen prior deformation. You can also see some interesting collapse features, this pit that formed right there. And you see some people mapping down in there. You also see a little white dot. This is another drone, 2 drones in the air here as well, doing some mapping. But hopefully you get a sense of here also in this uphill facing scarp environment, we get a lot of ponding. And so that would be useful indicator for the unusual deformation, but also you can see a beheaded channel. So right here, if you can see where my cursor is, or my mouse, you see this channel. Basically now flow can't really get across the scarp, but in the past it might have. So that's what we call a beheaded or defeated channel, and a wind gap. So only the wind blows through the gap now instead of any water flowing. So just a moment longer looking at these, the surface rupture from this magnitude 6 earthquake. So this is a relatively large amount of deformation for that size earthquake. So I'm going to keep going in the interest of time. So the last earthquake I'll talk about in the last 4 or 5 minutes is this earthquake that's further to the northeast. So it's really in the Tian Shan, not the Pamir Tian Shan convergence zone. And it's a zone 1911 earthquake. And so now this big lake is called the Issyk-Kul. And you can see between 1885 and 1911, there were several large earthquakes in this zone, basically magnitude 7.7 to 8 plus. So a huge amount of strain release for an intercontinental setting. And so the one that we worked on is this one shown with the red traces. That's called the 1911 Kebin earthquake. And this work was done with our colleagues from the Kyrgyz Institute of Seismology. And that's one of them there. She's working the total station. So you can tell when this work was originally done, which was like 2004. So we weren't droning at that time. So here you can see just a little bit of kind of thinking about some differences in surface rupture mapping. This is at a fairly, the whole scale. You see the scale to the upper right there. So my mapping, my compilation of our field work is very discontinuous, little tiny pieces of rupture that are preserved, whereas Delvaux and all, they drew kind of more continuous, which might have been a little bit more coarse mapping. And that's in contrast to then the 1914 mapping from Bogdanovich. So the Russian Tsar sent his chief engineer to this area, and they mapped kind of immediately after the earthquake. And so presumably that mapping would show the more continuous deformation, and our discontinuous work is because of almost 100 years of surface processes kind of wiping out the traces. So here's just a few pictures. You can see a repeat here, the upper right, there's the horses of Bogdanovich's team and the fault scarp. And then below, the lower right, is that same place in 2004. The rupture goes down the hill, and it is basically uplifted this river channel. And when we go down, we can see that same scarp that formed with one of these bohanka, this bread loaf truck for scale. And here's a view of that site. So you can see these terraces are being deformed. The flow is actually downstream to the right. So there would have been a waterfall here probably in that earthquake. And we think that the earthquake lifted up that channel floor by 6 to 8 meters. Here's a view kind of further along the rupture in this alpine environment. You can see the steep scarp and kind of simple field tracing of the scarp profiles. And then here's a landslide I put in for Chris. This is called the Ananyevo landslide. And this was one of the major sources of damage and unfortunately death in this earthquake, because it slid down and buried a village in that earthquake, but it's right on the ruptured trace. And then just to finish a couple more minutes. So this is kind of the same area I've just been showing. The Ananyevo landslide's a little bit hard to see. It's right in the middle here. But if we look up in this zone, this is a kind of complex rupture zone where the traces are changing quite a bit. So if you look at the red trace, you see it's a real step over in this complex thrust trace. And that would be quite difficult to anticipate if you didn't see decent amount of activity. So you kind of have to go back to the basics, try to track it. You can see again, probably a fair amount of landsliding on some of these thrust fronts. Here's another view of that zone. And I just wanted to make a point that here, we're looking uphill at a scarp that we infer to be from a reverse fault, but it is basically thrusting downhill. So the fault surface basically changes dip. And this, then no wonder there's a lot of interesting secondary deformation in the hanging wall, is because the hanging wall is basically being torn apart. What's important to see behind, though, is there's also a normal fault kind of fracture that was noted in 1911 there, and you can still see the scarps up here in the high topography. And here's a view with somebody there for scale. So it's like a 4-meter high free face that formed in that earthquake. And so this one, you could say, well, is this a Sakungen? Is this a proto landslide, or is it a normal fault? It's kind of limited to that ridge, so it's probably just a kind of proto landslide. It had normal slip dropping down into the deforming hanging wall, but it's not far from breaking loose probably and being another Ananyevo landslide. So with that, I'll stop, and hopefully you guys could see my screen okay. It has some weirdness in Zoom.
All right, great. Thank you very much, Ramon and Chris and Rich, for those presentations today. So we are out of time, but I just want to make 2 announcements, and then I want to stay for like 2 minutes with any questions, but I have to go pretty soon. Okay, so you have this assignment due on Monday, and it's asking you to look at a fault in Seattle. So just as a reminder, when you're doing this homework, you should be thinking about the fault activity at several scales. So at that smallest scale, probably a good way to start is to map those geomorphic features and try to approach the problem with very few preconceived notions about what's happening. But then as you draw your faults, as you connect those lines between those geomorphic features that you see, do want you to be getting to higher levels of interpretation. And then finally, at that highest level, you want to be thinking about those faults in relationship to what you saw today. How does the interpretation of different fault systems that Rich, Chris, and Ramon talked about today inform how you're going to interpret those faults? And then come back to my presentation about subduction zone systems and the earthquake cycle of deformation, and what are some expectations or ideas that you have about how this area in Seattle deforms, and how does that relate to the fact that Seattle is part of the subduction zone system. That's announcement 1. And then announcement 2 is please don't forget that Rachel is doing this really important study where she's looking at how people, and particularly students, can learn how to map and really hone their skills to be professional mappers. And so she's asking really not for that much, for you to agree for her to use the maps that you've already completed in her study. And so you can agree for her to use those maps by filling out the form that she sent yesterday. And then that's item 1, really easy. You don't have to spend any more time or minimal time to agree for her to use your maps. And then second, a little bit more time, but we would appreciate from you, is on the normal fault assignment, which is a few assignments away. If you take half an hour of time to meet with Rachel on Zoom and to essentially discuss with her, tell her your approach to fault mapping. And probably in the end, this actually will help you to map better, because you'll have that half an hour to really slow down and tell her how you're doing your mapping. So please, it is optional, but we would appreciate if you would agree to participate in ideally both parts of her study, but at least for her to use your already drawn maps in her study. Yes, so class is over, but if there are any questions, happy to take them quickly.